Hi and welcome. We're going to continue our exploration of Sylow's theorem, and this is exploration of Sylow's theorem, and this is exploration 12 of Sylow's theorem. So the general theorem says the following: suppose that G is a finite group whose order is p to the alpha times m, where GCD of p and m is equal to 1. That is, p and m are relatively prime. Does that imply that there exists some subgroup h of G such that order of h equals to p to the alpha? Right? That's the key question. Is this statement true? Now, we've been really exploring and thinking about this, and so far we appear to have proved the following. See if you buy it. So far we appear to have proved that if G is cyclic, and order of G is indeed p to the alpha times m, then this implies that there must exist some subgroup h of G such that order of h equals to p to the alpha. And we appear to have proved this statement, that we appear to have proved this special case. Notice it's a special case because G is being thought of as cyclic. No one says it has to be. And when we wrote the proof of this special case in the last video, we don't appear to have used the fact that the GCD of P and M equals to 1. That is, P and M are relatively prime. We don't appear to have used that piece of information. So perhaps we'll use it in the next part of the proof, because if we prove the statement is true when G is cyclic, now suppose we prove the following. Suppose we prove that if G isn't cyclic, suppose we prove this, that if G isn't cyclic and order of G equals to p to the alpha times m, can't we and let's say that we prove that if G is not cyclic and order of G equals to p to the alpha times m, that there exists some h subgroup of G such that order of h equals to p to the alpha. Would you agree that if we proved this statement, the second part of it, of course here we're not sure if it's true or not, if we prove the second part, given that we seem to have proved the first part, when G is cyclic, wouldn't we be done with our proof? So our question is to figure out, well, okay, fine, if G isn't cyclic, well, what's so special? How can we prove this second part, that if a group is not cyclic and the order of the group is p to the alpha times m, then there must exist a subgroup of order p to the alpha? And before, what we're doing was, first of all, let's see, what does saying that G is not cyclic, what does that give us? Why is that a useful piece of information? So one thing we noted is that, well, if G is not cyclic, then can we say the following, that, well, can we say that G has no generator? That is, for all G element of G, for all little G element of G, can we say that G never generates, little g never generates G? That is, no element of the group generates G. What else is true if a group is not cyclic? Can we also say that for all little g in G, order of little g never equals to p to the alpha times m? Can we say that? Okay. Because what do you think would happen if order of G were p to the alpha times m? Wouldn't little g then generate the entire group? Alright. What else can we conclude if a group is not cyclic? So, in this particular case, if order of G can never equal to p to the alpha times m, but order of G actually divides the order of the group, then do you mean that order of G must divide p to the alpha times m? According to Lagrange's theorem, if order of little g divides p to the alpha times m, can't we say then that order of G must be less than p to the alpha times m? Okay. If order of g divides p to the alpha times m and order of g does not equal to p to the alpha times m, can we say that order of little g is less than p to the alpha times m? Here, we're talking about little g. Okay, so we want to be careful. Little g and big G. Big G is a group. Little g is the element of the group. Little g. So, all right, fine. So if the group is not cyclic, then we're saying for all elements, little g and big G, order of little g is always less than p to the alpha times m. Okay, so what? What else can we say? Um, what else can we say about a group that is not cyclic? There seem to be some pretty obvious things. Like if G is not cyclic, then can we say that G is not isomorphic to Z mod P to the alpha times mz, right? Not isomorphic to it. Okay. Is any of this information useful to us? Well, before we seem to have been onto something, let's see if we can get back to that. Well, yeah, the isomorphism, not being isomorphic, is nice to know, but wondering how it's useful to proving our case here, our theorem in this special case. But we've been exploring before that order of G has to equal to, given that the order of every element divides the order of the group, order of little g has to be of the form p to the I times some L, where we said that L divides M, and well, I is just some natural number between what? Between alpha and 0. Okay. Well, so the idea was, maybe suppose we're able to show that there exists some, let's say what, k element of G such that order of k suppose we're somehow able to force the fact that for some k element of G, order of k actually equals to p to the alpha, right, times some little l. So like some times some little l. That is, the power of I is, and the power of p remains the same, but only l goes down. That is, l is some proper divisor of m. Suppose we're able to prove this, that there is an element like this such that order of k equals to p to the alpha times some l, where the p to the alpha has been kept constant. It's only the l, the divisor of m, that's been reduced. Well, or the m has been reduced. Well, suppose we're able to show this. Could this be useful information to us? Well, if we're able to prove this case, couldn't we conclude the following? That if we have an element whose order is p to the alpha times l, can't we say that, well, this is a subgroup of G, right? Order of k is a subgroup of G, isn't it? The subgroup generated by little k, it's a subgroup of G, and it's a weird subgroup in the sense that this subgroup K, this subgroup generated by K, well, it has order p to the alpha, right? Doesn't this cyclic subgroup have order p to the alpha times L? Okay. But if we have a cyclic group, right, a subgroup is still a group, isn't it? So, haven't we just found a group that is cyclic and has order p to the alpha times L? Right? Doesn't this information allow us to conclude, right, by our first part, the first part we proved before, the first special case, that if a group is cyclic and of the form p to the alpha times m, then there's a subgroup H of the group that has order p to the alpha. So now we found some group K, which happens to be a subgroup of G. Its order is p to the alpha times L, and we're saying that, well, isn't this group that's generated by K cyclic? Okay, if it is cyclic, then it has order p to the alpha times L. Doesn't our theorem then guarantee us that there exists some L subgroup of the subgroup generated by K, for which, so let's write this correctly, for which order of L actually turns out to be p to the alpha, right? And now the thing is, if L is a subgroup of K, or if L is a subgroup of the subgroup generated by K, and the subgroup generated by K is a subgroup of G, aren't we saying that L is also a subgroup of G, right? Because didn't we say that the subgroup generated by K is also a subgroup of G? So aren't we saying that L is a subgroup of G? So haven't we then found a subgroup L of G whose order is p to the alpha? Okay, so this is all well and good, but what's the problem with this argument? Well, the problem is, can we say this, that how do we know, right? The question is, how do we know that if the group is not cyclic, there must be some element little k of G whose order is p to the alpha times L? That is, that p to the alpha remains the same and we have some little power L, right? So this leads us to trying to prove this theorem. Suppose we prove this instead. Suppose we prove that, let's see if you buy it. Let's suppose we prove this, that if G is not cyclic, okay, the pen's misbehaving. So let's see. So this seems to be giving us some other roadmap towards solving the problem. Unless we've made an error, we don't appear to have. Indeed, if we had an element of order k, blah blah blah, yes, subgroup will be generated by little k will be that. You'll have a subgroup order p to the alpha. So let's see. Suppose, can we say that our problem now reduces to proving the following, that if G is cyclic, and order of G, sorry, if G is not cyclic, and order of G equals to p to the alpha times m, where p and m are relatively prime, then all of this implies then there exists some little g element of big G such that order of little g equals to p to the alpha times L, where L divides m. Right. Suppose we proved this claim here. If we're able to prove that if a group is not cyclic and there's an element of order p to the alpha times m and p and m are relatively prime, suppose all of that information guarantees us that we have some element little g such whose order is p to the alpha times L. Wouldn't we be done with our problem here? Here, instead of, before we argued using little k, but now we're arguing using little g. So let's try and see if we can prove this statement, okay? A group is not cyclic and it has, right, so we've been exploring the consequences of having a group not being cyclic. And so the true question becomes, how can we guarantee that there exists some little g in G such that order of G equals to p to the alpha times L? How can we guarantee this? What strategies are there for showing that there's an element whose order is p to the alpha times L? Right? So and remember, we haven't used the fact that p and m are relatively prime, so maybe that needs to come into the picture somehow. If p and m are relatively prime, what does that mean? Well, okay, if p and m are relatively prime, aren't we saying that well, they have no factors in common, right? So the only factor they have in common is 1. Okay, so what? Okay, so since P is a prime, right, can we say that P is not 1? Okay, so are we also saying that P does not divide M? Can we conclude that? Okay. And we said before, if M equals to 1, don't we just have that order of G equals to P to the alpha? And aren't we done there already? If we have a group whose order is P to the alpha, aren't we guaranteed a subgroup of order P to the alpha? Namely G. Isn't a group a subgroup of itself? So are we right then in assuming that, well, if I mean, if we avoid the trivial case where M equals to 1 and M is some number greater than 1, and we're also saying that M does not divide M, right? If we say that the GCD of P and M is 1, and we're saying that P does not divide M and M does not divide P, sorry. M does not divide P, okay? Is there anything else? Well, before we'd come up with some other ideas that really P is also an element of Z mod MZ star. That is the group of elements, the group of integers mod M, which are relatively prime to M, right? Whatever that group is, P is an element of it, isn't it? Because P and M are relatively prime. Okay, can't we also say then that M is an element of Z mod PZ star? Okay, that's kind of like Z mod PZ without 0. All elements relatively prime to P that are considered mod P, right? Right, and it's a group under multiplication here. So, sure. What else does it mean to say that P and M are relatively prime? Can we also say that M, if M does not divide P, can M possibly divide P to the alpha, right? Is that possible? Okay. How about this? Can P to the alpha possibly divide M, right? If P does not divide M, right? So we're saying that M does not divide P to the alpha and P to the alpha does not divide M. Okay. What else does it mean for P and M to be relatively prime? Can you think of something else? Alright, so let's see. Okay, we're trying to deal with a special case here. Perhaps we may not, it might be hard to find an element of order P to the alpha, but it may be easy to find an element of order P to the alpha times L, or to guarantee that such an element must exist. But, right, how do we show this? Um, Given that P and M are relatively prime, okay. So, maybe another thing to conclude is, if P is relatively prime to M, if P and M are relatively prime, and L is some divisor of M, can we say that the GCD of P and L also equals to 1? That is, P and L are also relatively prime? Okay. Oh, wow. Oh, this is bizarre, isn't it? So, maybe even something else we can conclude, which, again, unsure how this is useful, but it may give us something here. Right? Remember we said before that, well, P is an element of, was it the other way around? Let's see. We said that M is an element of Z mod PZ star, right? It's an element of that group under multiplication because M is relatively prime to P. Well, can we say the following in fact, that the set of all divisors of M, that is the set of all L such that L divides M, is actually a subset. All L such that L divide M, that set of all divisors of M is also actually a subset of Z mod PZ star. Can we say that? Okay. But yeah. So what? So what? Is there anything special about concluding that every divisor of M is an element of Z mod PZ star? Okay. Alright, we just run out of time, so let's just take a short break. We'll be back and focus more on let's see where this line of reasoning takes us. Either it takes us somewhere or it tells us that it's definitely not taking us anywhere, in which case we'll pursue another avenue. Otherwise, thanks for watching this video. Have a relentless week. Bye.